Hi everyone, welcome to the second public lecture for our ESRC funded climate ethics and climate economics workshop on risk, uncertainty and catastrophe scenarios. Tonight we're joined by Hilary Greaves. Hilary is a philosopher at the University of Oxford, and although she works in moral philosophy, she is I can attest as having been her postdoc, she's a very practically minded philosopher who wants to change the world. Tonight she's going to be talking about the vexed issue of whether or not population, and particularly population growth, or indeed population decline, can be seen as an important factor when we consider how we should understand and adapt to climate change. So, thank you very much, Hilary.
So I'm glad Simon thinks it's a vexed issue. I was actually going to start by saying the topic of my talk is a question that most people will probably consider so obvious as to not be worth discussing. So I'm impressed that some of you have come here at least. So it's the question of whether overpopulation really is, after all, one of the drivers of climate change, as we're so often told. So, as we all know, climate change is driven by emissions of greenhouse gases, notably emissions of carbon dioxide, and as we also all know, the emissions rate of greenhouse gases have been significantly on the rise over the past few decades. So here's a graph from one of the recent-ish IPCC reports, which shows that the total global emissions rate of greenhouse gases has roughly doubled in the 40-year period from 1970 to 2010. Now, commentators differ somewhat in their tendency to point the finger of blame for this on growth in population size on the one hand, or growth in the average per capita emissions rate on the other hand. So as we also all know, population size has been growing rapidly over the period in question and is projected to continue to grow well into the present century. And it's also the case that living standards have been sharply on the rise, and insofar as that is driven by the industrialisation of more and more countries, that is generally going to correlate with a rise in the per capita emissions rate of greenhouse gases. For the purposes of my talk, I don't really need to take a stance on where we should point the finger of blame particularly. The simple mathematical fact is that the total global emissions rate is the product of the total global population size and the average global per capita emissions rate, so that a given proportional increase in either of these two factors equally generates the same size proportional increase in the total global emissions rate when the other factor is held fixed. So at any rate then, it seems that insofar as we have a goal of mitigating climate change, and therefore perhaps insofar as we have a goal of reducing the total emissions rate, reducing population size relative to business as usual seems like one sensible thing to try, doesn't it? So this line of thought is often heard. I want to cast the light of sort of questioning on this matter. Is it really the case that reducing population size would help with climate change? And if so, how exactly? I'm raising that question because I think this is actually a lot less obvious than is normally supposed. Here's the apparently obvious, simple line of argument for a positive answer, which I've seen most clearly expressed in the writing of Jonathan Porritt. But I pick on Porritt only because he's the person who's done us the service of stating this most clearly and explicitly. I take it the basic line of thought is often expressed. Porritt says, look, at one level, this is all about basic mathematics. We roughly know the total volume of greenhouse gases we can put into the atmosphere over the next few decades if we are to stay the right side of the 2 degrees centigrade increase by the end of the century, which scientists tell us we absolutely mustn't go above. That total volume has to be divided up between the total number of people doing the emitting. And then he continues, I believe it's part of our duty to the next generation to advance the compassionate, progressive case for a full-on campaign to put the world on a downward population trajectory just as fast as we can. So that's in an article in the New Internationalist from 2010. So the point I'm going to try to urge in my talk is not necessarily that overpopulation is not a driver of climate change. I think at the end of the day that it probably is. In that sense, I agree with Porritt's eventual conclusion, tentatively. But I think that the arguments that lead to that conclusion are significantly more complicated than Porritt and others are giving them credit for. And it's important to focus on the right factors, otherwise the debate is going to get confused and taken in wrong directions. My central point is going to be this argument focuses essentially on the emissions rate. It obsesses about, for example, how much greenhouse gases we put into the atmosphere specifically over the next few decades and how much climate change we get specifically by the end of the century. And I'm going to be arguing that those things are red herrings. Those things are going to tend to take the discussion in an unhelpful direction. So here's an outline of the rest of the talk. The basic point that I'm seizing on in critiquing the Parrot argument is a basic but now very widely accepted fact about climate science, and it's to do with the significance of cumulative emissions over the emissions rate at any given time. So in section 1, I'll lay out how that bit of climate science goes. In section 2, I want to suggest that, given this fact about climate science, an illuminating way to think about what it is that we're doing when we talk about reducing the population size relative to some status quo is we are making it the case that a given number of people, let's say the next billion people to be born, get spaced out more across a longer stretch of time. So there's a sense then in which reducing population size isn't really reducing population size in perhaps a relevant sense. It's stretching out the same size population over a longer period of time. And in the light of the point about cumulative emissions, it's not at all obvious, at least it's not just a matter of basic mathematics, that this is actually going to help. So having made that basic suggestion, I'll then sketch a simple model such that if this simple model were an accurate depiction of what would result from reducing population sizes, then I will claim reducing population sizes wouldn't help with climate change. In section 3, I'll survey 2 bad arguments which will take issue with that conditional claim I just made. So these are going to be arguments, attempted arguments for the claim that even if the simple model were right, even if that accurately captures what would be going on when we reduce population sizes, still that would count as an improvement. So I think these arguments are kind of tempting, but I think they're bad, so I'll say what they are and why I think they're wrong. Then in section 4, I'll introduce the considerations that I think are where the action really is in this debate. These are the questions I think we need to be focusing on if we want to see the relationship between population sizes and mitigating climate change. These are matters of whether the assumptions of my simple model really are correct. And I think there are good reasons for thinking they're incorrect in important ways. So this is why I end up agreeing at the end of the day that probably reducing population size would help, but not for the reasons that people like Parrot give. Okay, so firstly then, the point about cumulative emissions. I want to talk about emissions pathways and I want to talk about temperature pathways. So here are just some graphs to illustrate these concepts. An emissions pathway tells you what the total global emissions rate is of greenhouse gases at every given point in time between, say, the year 2000 and the year 2100. So these things are going to project into the future. We can consider various possible emission scenarios corresponding to different emissions pathways. One of the things we're ultimately interested in, well, close to ultimately interested in, is the temperature pathway. This is a thing that tells us what the global mean surface temperature is going to be at every point in time. And of course, there are various different possibilities for that. One of the things we want from our climate science is a function that maps us from the emissions pathways to the temperature pathways. So these are a couple of corresponding graphs from one of the IPCC reports where the authors consider various possible emission scenarios and then give the median estimate for what the corresponding temperature pathway would be if that emission scenario were realised. A thing you'll notice about this graph is that the range of emission scenarios that have been considered have the property that you can generally order them in terms of higher and lower emissions without paying particular attention to the shapes of the graphs. Generally speaking, with a couple of exceptions in these cases, these emissions pathways that have higher emissions rate at one time also have higher emissions rates at other times. Those are the ones that are just higher emissions full stop. So unsurprisingly then, generally speaking, for the pathways that have higher emissions full stop in that sense, you also get more temperature rise full stop when you do the mapping across. For the point about cumulative emissions, we need to consider emission scenarios that differ from one another in a more subtle and interesting way. So this graph on the left here is a figure from a 2009 paper by Miles Allen and collaborators. So this is one of the central papers in which the point about cumulative emissions is pushed. Look at the red and the orange lines in that graph on the left. These represent 50 different possible emission scenarios. They differ from one another over the timing of emissions. So if you ask, for instance, what's the emissions rate in 2040, these scenarios will give different answers from one another to that question. However, they share one very important feature, which is the area under each of these 50 graphs is exactly the same. So these are 50 different emission scenarios which have the same cumulative emissions as one another. What Alan and his collaborators discover when they run the climate models on this set of emission scenarios is that insofar as the thing that you're interested in is the peak number of degrees of warming you get in the corresponding temperature pathway, it makes no difference which of these 50 emission scenarios you pick. So if you fix the cumulative emissions, little variations to the timing of emissions at earlier and later times, consistent with the same fact about what the cumulative emissions are, do not change even this probability profile of how many degrees of eventual warming you're going to get. So in this graph on the right, where they've graphed the probability density function against the number of degrees of peak warming, there are actually 50 graphs drawn there corresponding to the 50 curves on the left, but you can only really see one because they're exactly on top of one another. So peak warming then is determined by cumulative emissions alone, independently of other details of the emissions pathway. I think that's important, and I think the debate about the relevance of population size has failed to take adequate account of this point. So now let me try to start convincing you of that. Section 2, this concept I want to introduce of population spreading, and then my simple model where I said, okay, if this simple model were an accurate description of what would happen when we reduce population, I claim reducing population wouldn't help with climate change. Okay, so this next slide is a little bit more technical. I apologise for the text density. Let A be any state of affairs. You can think of it as business as usual, the status quo. And by state of affairs here, I mean a timeless object, so a complete history of the world from Big Bang to heat death, rather than a snapshot of the world at a given instant of time. Now let B be another state of affairs, and let's suppose that B is related to A in the following way. So heuristically, what these conditions are trying to say is, what you've done in going from B to A is you've stretched out the population for the rest of the future over a longer period of time, but you haven't changed the number of people who ever live, you just spaced them out more across time. That's what the definition's trying to get at. For people who like to see the actual definition, though, here goes. Let B be related to A in such a way that there's some bijection, call it pi, from the set of people who ever exist, that is the timeless population in the first state of affairs, to the set of people who ever exist in the second state of affairs with the following properties. First property, for every person X who exists in the first state of affairs A, the life that that person lives in A and the life that the corresponding person pi of X lives in B is equally long. Secondly, suppose that this bijection respects the birth order, that is to say, it maps the first person born in A to the first person born in B and the second person born in A to the second person born in B and so forth. It doesn't jumble up the order. Thirdly, suppose that this bijection increases the birth spacing. So if X and Y are two people in A and they're born 1 second apart, then pi of X and pi of Y will also be two people who are consecutively born in B, but they'll be born more than 1 second apart in B. When these conditions obtain, what we've done in going from A to B is we've reduced the instantaneous population size at any given time. In that sense, we've reduced population. But we haven't reduced the timeless population. We have not affected the number of people who ever live. I just stipulated that when I said that this is a bijection from the whole timeless population in A to the whole timeless population in B. So there's one sense in which we've reduced population size. There's another sense in which we haven't. When these conditions obtain, let me say that by definition, B is obtained from A by population spreading. Okay, that's just my definition. Let me make a further definition. If in addition to all of that stuff, this mapping from the people in A to the people in B preserves lifetime carbon emissions, so if it's the case, for example, that the amount of carbon the 564th person in A emits over the course of her lifetime is the same as the amount of carbon that the 564th person in B emits over the course of his lifetime, then say that B is related to A by mere population spreading. So we have merely spread people out more thinly across time in going from A to B. We've done so in a way in particular that didn't affect individuals' lifetime carbon emissions. Why is this an interesting definition for the purposes of the present discussion? Well, because if B is related to A in this way, then going from A to B, although it's reduced population size in one sense, has not made any difference at all to cumulative emissions. And so insofar as cumulative emissions are the things that we care about for the purposes of climate change, we haven't improved the things we care about for the purpose of climate change. So now we've got the concepts that we need to set up my simple model. So I emphasise I'm not asserting that these conditions do obtain, and indeed later in the talk I'm going to say that two of them in particular probably don't. But if these conditions obtained, then I claim reducing population size wouldn't help. So the first claim is, or the first assumption of the model rather, is that reducing instantaneous population size, the way we would in fact do it if we were try to reduce populations, would implement mere population spreading. I'll say more about the climate era thing in a minute. Second assumption, Allen and co-authors are correct, that is to say peak warming is determined by cumulative emissions alone. Third assumption, this is the thing we care about, i.e. climate change damages are a function of the height of the warming peak alone. So I claim that if all of these three things hold, then reducing instantaneous population size wouldn't reduce climate change damages. Well, actually, that's more than a mere claim. That just about follows as a matter of logic from those three assumptions, given that mere population spreading doesn't affect cumulative emissions. And then I further claim that if you don't reduce climate change damages, in the sense that you get from this argument, you haven't improved things. So my diagnosis then with what's wrong with the arguments that Parrot and people like him are offering is that they're focusing too closely on the emissions rates. And that's essential to their argument. They wouldn't be able to make their argument if they zoomed in instead on cumulative emissions instead of emissions rates. But once we do recognise that point about cumulative emissions, then we should be deeply suspicious of any argument that can only be stated in terms of emissions rates. Okay, now I want to say why I had climate era in brackets here. If you only want the kind of general gist of my talk, you can glaze over on this next slide. But it's somewhat important for me in the bigger picture. So the point of this modification is the first assumption of my model there is actually stronger than I need, and it's also strong in a way that makes it completely implausible, and completely implausible for reasons that are irrelevant to my argument. So I want to weaken it to make it more plausible, but the weakening, again, is not going to affect this simple model. The point is that the way I defined population spreading and mere population spreading, you don't count as doing population spreading unless you're holding fixed the timeless population. In fact, it's totally implausible that reducing the instantaneous population size, the number of people who live at any one time in the short to medium term, would leave unaffected the number of people who ever live. I don't know what the sign of the effect will be. It could be that reducing instantaneous population size in the short term reduces the number of people who are ever going to live because, let's say, some unforeseen event is going to come and wipe us all out in 2200 no matter what. And so if we have fewer people living in the short term, we just succeed in fitting in fewer people before this apocalypse. That's one possibility. Another possibility which would push in the other direction is, well, maybe having too many people on the planet in the short term increases existential risks and so decreases the number of people who ever get to live. That's quite possible too. I don't know which of those effects is going to dominate, but I am pretty sure that reducing instantaneous population size would not leave the number of people who ever live completely unaffected. So I don't really want a model that assumes that it does, and I don't really need a model that assumes that it does. And this is the feature the slightly more complicated version is going to remove. So let me define the notion of a climate change era. This is supposed to be a time period during which the vast majority of carbon emissions occur. So the point here is, if only because the carbon reserves that are in the ground are finite, there's going to have to come a point in time, some distance in the future, maybe we know when, we know not when, after which carbon emissions are going to be negligible. So let me call this date T end. In any given state of affairs, you can identify a corresponding T end that marks the end of the climate change era in this sense. Now for my states of affairs A and B, where A is the state of affairs with the higher instantaneous populations and B is the state of affairs with the lower instantaneous populations, I can say all that stuff about population spreading only within the climate change eras in the two states of affairs. So now, in contrast to the original definition, let me let this bijection pi be a bijection not from the set of people who ever exist in A to the set of people who ever exist in B, but rather it's just a bijection from some subset of the people who exist in A to some subset of the people who exist in B, and furthermore, all the people who live in the climate change era in either A or B get to be in respectively the domain or the range of this bijection. So now what we're doing in going from A to B is spreading people out more thinly across time during the climate change era, but we're now saying nothing about what happens after that. So in particular, we're not presupposing that the number of people who ever get to exist is held fixed in going from A to B. Okay, so if the bijection has all the properties that it has before, except that it only has to be a bijection during this climate change era, then let me say that B is related to A by mere climate era population spreading. So I said that this is not going to affect the simple model. Why is that? Well, because the key feature of this concept of mere population spreading for the purposes of my simple model was that it left cumulative emissions unaffected. And mere climate era population spreading, as defined here, is also going to leave cumulative emissions basically unaffected. Because if the climate change era includes all the times during which any significant carbon emissions are happening, then it doesn't make any significant difference to cumulative emissions what happens outside of that period. Okay, so the official version of the simple model has this slightly more complicated concept of population spreading in it. Okay, so I said you could glaze over if you didn't want the details. Now you can unglaze again. I also want to introduce another concept which I have found very helpful for thinking through these matters without getting hopelessly confused. This is a concept of what I'm going to call population time. So the idea is that population time, I stipulate, is a modification of ordinary physical time. Ordinary physical time is the thing that's measured by the clock on the wall and the revolutions of the Earth around the Sun and the oscillations of the cesium atom and all that normal stuff. I'm stipulating that the amount of population time that passes between any two instants, like those two, is equal to the amount of physical time that passes between those two instants multiplied by the instantaneous population size at the time in question. What does this notion of time do? Well, it means, among other things, that what you do if you increase the instantaneous population size is that you speed up the rate at which the population clock ticks relative to the physical clock. Similarly, if you reduce the instantaneous population size, you slow down the population clock relative to the physical clock. So using this notion, we can now frame some hypotheses, raise some questions which we didn't previously have the conceptual resources to state. For example, the thing that the Parrot argument is seizing on is the pretty obvious fact that reducing instantaneous population sizes would slow down emissions rates relative to physical time. Now we can ask, okay, but hang on, Professor Parrot, would it also slow down emissions rates relative to population time? That's far less obvious. And it's also very far from obvious that emissions rates relative to physical time are the thing we should care about, as opposed to emissions rates relative to population time, insofar as we should even be talking about emissions rates at all. Let me also give you a partial analogy, which may or may not be helpful, but again, it's a thing that I've found helpful for seeing how these alternative, made-up, non-standard notions of time can be illuminating and clarifying arguments. So I want to consider the decay of playground equipment. I don't want to think about the effects of the weather. So let me stipulate I'm talking about an indoor playground where the thing that's causing the decay of the playground equipment is just all these children who keep running around on it and hitting it and climbing it and so forth. Suppose it's observed that some particular playground seems to be falling to bits more quickly than the maintainers had anticipated. One can imagine some completely misguided campaigner arguing as follows. Look, we should impose quotas on the number of children who are allowed to play on the playground on any given day, because this playground is decaying too quickly. And if we make a rule that says no more than 25 children are allowed to play on any given day, then we can slow down the rate of decay of this playground equipment. Okay, so I'm claiming this argument is totally misguided. Why is it totally misguided? Well, one way of saying why it's wrong is, of course, that the whole point of a playground is to be played on by kids. Another way of saying what's wrong with it, though, is to observe that, well, let me now define another alternative notion of time, usage time. Usage time is like population time, except that instead of multiplying physical time by number of people on the planet, you multiply physical time by the number of children playing on the playground at the time in question. So this usage time clock is one that stops overnight when all the children go to bed, starts again in the morning when the first children arrive, and ticks faster when the playground is populated by more children. Given that concept, we can now say, okay, look, Mrs. Campaigner, you're confused. What you're pointing out, which is quite true, is that if you introduce your quotas, you'll slow down the rate of decay of the playground in physical time, but we just don't care about that kind of rate. You won't, or at least you haven't given us any reason for thinking that you will, slow down the rate of decay of the playground equipment in usage time, and that's the thing we care about. If you could suggest something that would slow down the decay rate in usage time, like, for example, using stronger bolts or better protective paint, there might be a genuine case for doing that. But don't claim that we care about the decay rate in physical time per se. Physical time is not really a normatively relevant thing. So anyway, I of course don't claim that this analogy is perfect, the analogy between the playground and the case of climate change. No analogy is perfect. But I do think it's somewhat illuminating. I do think there's a danger that people who argue in the way that Parrot does are making a mistake that's at least somewhat similar to the mistake that my misguided campaigner is making. If you don't find that analogy helpful, just forget it, but remember the notion of population time, because I'm going to use that in what follows. Okay, so to recap where we've got to then, I had this simple model. I claimed that if all the assumptions of this simple model were true, then reducing population size wouldn't help. Next, I want to consider two arguments that I'm going to say are bad ones for denying even that conditional claim before I go on to examine whether these assumptions of the model are actually true. Okay, so first the bad arguments. These are going to be reasons one might give for thinking that actually, as a matter of fundamental evaluative theory, physical time does have fundamental normative importance, and because of that, even if reducing population size would merely slow down the process of climate change in physical time in a way that in some sense didn't affect the climate damages, just making those damages happen later in time would itself be a good thing, according to these two arguments, but I think both the arguments are wrong, as I said. Okay, so what are the two arguments? The first one appeals to a theory of value, which I'm going to call instantaneous averagism. So I've made up the name, but I haven't made up the view. This is a view that's quite commonly used in some economic models. So this is a view that says, okay, if you want to construct an index of how good a given state of affairs is overall, again, complete history of the world type state of affairs, here's what you should do. First, you should look at every instant of time taken separately, and you should calculate the average well-being level at that instant of time. And then secondly, you should sum, or if you like, integrate the resulting quantities across all of time. So you take the time integral of the average goodness of people's lives at that instant in time, according to this theory. If you're thinking that way, then you might think, oh, well, it would be good even if we merely slowed down climate change, even if we did it in a way that did not affect, say, the number or the severity of the eventual storms and droughts and sea level rises and so forth, because at least we will have pushed these bad things further into the future. So then perhaps one might continue. At least we will have made it the case that we've increased the duration of time during which humanity gets to enjoy the relatively benign conditions that precede the onset of serious climate change, and we've decreased the interval of time, perhaps, during which humanity has to suffer the adverse consequences of climate change. Well, that argument would need to be made more precise. We could do that thing, making it more precise, if we thought it was worth the effort. I'm not going to do that, though, because I think the more important point to note is that the theory of value that this way of thinking essentially starts from is completely implausible. So I want to emphasize this because, as I said, I think this model of value is often used in certain bits of the economics literature, and the criticisms are ones that are sort of fairly well known, but their force is not sufficiently appreciated. One way of saying what's wrong with it is that this theory conflicts with an anonymized version of the Pareto principle. So this is language that will make sense to economists. The Pareto principle just says if two states of affairs are related in such a way that no person is made better off in going from state of affairs A to B, and at least one person is made worse off, then B is worse than A. An anonymized version of that Pareto principle would say, well, never mind the particular identities of the people concerned, maybe it's different people who live in A than in B, but if you can find some way of mapping the A people to the B people, such that for every person in A, the corresponding person in B has at least as high welfare. Sorry, which way did I say it? Anyway, if the mapping is such that for every person in A, the corresponding person in B has at least as high welfare in A as their counterpart did in B, as their counterpart did in A, and sometimes the B person has higher welfare than the counterpart person in A, then B is better than A. If you've got a theory that conflicts with this principle, most economists would agree that's a sufficient condition for the theory being chucked out. But insofar as there's a problem with Pareto principles, it's that they're too weak, they don't tell us enough. But when the Pareto principle does issue a definite verdict, most people would agree you have to respect that verdict. One way of seeing how this theory ends up violating this anonymized Pareto principle, it may be the most blatant and egregious and obviously misguided thing it implies, concerns premature death or killing off the worst off people. So to take a simple scenario to make the case vivid, consider a universe that only contains two people, Annie and Bob. Suppose they both live for 100 years in state of affairs A, and they live at the same time as one another. So they're both born in, say, the year 2000, they both die in the year 2100. Suppose that they both have extremely good lives for the whole of this period, but Annie's life is slightly better than Bob's. So at every point in time, let's say Annie has a well-being level of 100, and Bob has a well-being level of merely 99. According to this theory, you would make the state of affairs better if you killed Bob at, say, the age of 10, because that would mean that for the remaining 90 years, the average well-being level averaged across the people who then exist will be 100 rather than only 99.5. So according to this theory, you make things better if you kill off Bob, but that's obviously implausible. Bob is not doing any harm. You don't improve Annie's life by killing off Bob. It's a bad thing to kill him off. So that's a way of seeing why this theory of value is like fundamentally mistaken. And given that it's so fundamentally mistaken, I'm not particularly interested in making more precise and examining the details of how this argument based on this theory of value might go. Okay, second bad argument. This would appeal to the idea of pure discounting. So this is the idea, popular among some but not all economists, that a given amount of well-being matters less the further into the future it occurs. So for example, if you like the formulae, this is how you might write down the maths of this value function. We're again going to add things up across times because we don't want to run into the same problems that the previous theory had. The thing we're adding up across times is not going to be any version of the average well-being level at that time. It's going to be a version of the total well-being at that time. However, we're going to discount. So we're going to add this extra factor, delta t, which gets smaller as t gets larger. Okay, so if you have that theory, then you might think, oh, well, again, I've got a reason for thinking I would improve the state of affairs even if I merely slowed down climate change in physical time, again, without changing the nature and severity of the climate damages that eventually occur, because at least I make them happen further in the future. And now I've got a theory of value that says bad things that happen further in the future don't matter as much from the normative point of view as bad things that happen in the nearer future. Okay, so as a matter of fact, I think it's wrong to carry out pure discounting. This is a matter of well-worn debate. Unfortunately, I don't have to get into it, because even if you did accept this theory of value, it would not in fact have the consequence that merely slowing down climate change would be an improvement. In fact, it would have a consequence that merely slowing down climate change in the way we've been talking about would amount to making things worse. Why is that? Well, that's going to follow if you think, as most people do, that even with the climate change damages in place, lives will still on average be worth living. Well-being levels will still on average be positive. They just won't be as high as they would have been in the absence of climate change. If that's true, then the crucial thing from the point of view of this argument is, yeah, sure, if you slow down climate change in physical time, you push the climate change damages further into the future. But you also push a bunch of positive well-being further into the future. You have to take account of that too. And if you think that the net effect, when you add up the positive well-being in people's lives and then you subtract the climate damages, if you think the net value after you've taken account of all of that stuff is positive, then ultimately what you've done is shifted a bunch of positive stuff further into the future, where according to this theory of value, it then matters less. So, conclusion, even if you buy the idea of pure discounting, it will not get you this initially perhaps intuitive thing that shifting climate change damages further into the future itself constitutes an improvement. So although my talk of climate change damages so far has been pretty loose and hand-wavy, I think the conditional claim I made earlier is correct. If the assumptions of the simple model were correct, so that in the sense that you get from that model, merely reducing instantaneous population size would merely slow down climate change in a way that doesn't change the climate change damages, then reducing population size wouldn't have generated any improvement. So I think the important questions instead are in this matter of whether the assumptions of the simple model really are correct. Is that an accurate representation of what would in fact happen if we reduced population sizes in the kind of ways that we would be able to if we wanted to? Okay, so I think the answers are no, and in particular I think the answers are probably no for 2, at least, of the 3 assumptions of the simple model. So just by way of recap, here are those assumptions again. The first one was that reducing instantaneous population size would implement mere climate-era population spreading. That is, it would just space people out more thinly across time during the climate change era. It wouldn't affect lifetime carbon emissions for the nth person for any number n. Second assumption, Alan et al. Were correct, i.e. peak warming is determined by cumulative emissions alone. And third assumption, climate change damages are a function of the height of the warming peak alone. Okay, I'm not going to question the second assumption here, although we could. I'm going to focus on the first and the third, because I think there clearly are reasons for doubting the first and the third assumptions, and particularly there are reasons for doubting the first and the third assumptions in ways that do, at the end of the day, tend to favour population reduction. Okay, so how do these things go? So first, the possibility that that first assumption is false. Okay, so the first assumption again was reducing instantaneous population size would merely implement mere climate-era population spreading, wouldn't change the individual lifetime emissions, and so wouldn't change the cumulative emissions. Why do I think that's likely to be false? The most salient factor concerns renewable energy resources. Let's suppose we hold fixed the lifetime energy consumption of the nth person for every n when we go from A to B. Well, it doesn't immediately follow we've held fixed the lifetime carbon emissions, because a given person can meet her energy consumption needs from a combination of carbon energy sources and renewable energy resources. However, here we see one way in which physical time might actually be important as a matter of the causal structure of the world, because the planet supplies a fixed amount of a given renewable energy source, let's say solar energy or wind or tidal, per unit physical time. That's the way the planet works. It doesn't supply a fixed amount of renewable energy per unit population time, when you vary population in particular. Because of this, one thing you would do if you reduced instantaneous population size is you make it the case that on average each individual person can have a larger share of renewable energy sources than they could in the case where the population was larger. You've got this fixed flow of renewable energy sources. You can now divide that flow up between fewer people. So because of that, if you're holding fixed energy consumption needs when you go from A to B, you are likely to reduce lifetime carbon emissions of the nth person when you go from A to B. That's the basic story. It's a bit more complicated than this, because, for example, the renewable energy supply is not actually something that's just fixed by the planet completely independently of what the population is up to. In the example of solar energy, for example, certainly at the moment the thing that constrains how much solar energy we're able to harness is not so much the sheer amount of solar energy that is influxing into the Earth system, it's rather the number and the efficiency of the solar panels that we have. And notice that these are things that are made and developed by people. So we need to investigate the line of thought that having fewer people on the planet would slow down the rate at which the situation vis-a-vis number and efficiency of solar panels can be improved. And so this is the kind of thing that makes the argument a bit more complicated than I sketched, and we do need to take these things into account. This makes it not completely obvious whether, in fact, at the end of the day, reducing instantaneous population sizes would reduce lifetime carbon emissions. But my conjecture is that even when you take those complications into account, the simple argument ends up being the dominant factor. So reducing instantaneous population sizes, I conjecture, would indeed reduce lifetime carbon emissions, and so would reduce cumulative emissions. Okay, so that's one thing. The second thing is about adaptation. So recall the third assumption of my simple model. That was the assumption that climate change damages are a function of the height of the warming peak alone. Why do I think that's false? So this is false because we don't ultimately care about the amount of climate change per se, in any sort of physically natural sense of climate change. We ultimately care about the extent to which climate change reduces well-being levels. And that's a matter of how much adaptation we're able to carry out, not only a matter of how much climate change has happened. And then crucially, the further factor is this process of adaptation. I mean, it depends on the details, it depends which particular adaptation process you're talking about, but many processes of adaptation are constrained specifically in physical time rather than in population time, just because of the nature of the causal process we're talking about. So let me give you two examples of that, cases where it looks as though the process of adaptation is going to be constrained by physical time in such a way that actually slowing down climate change in physical time does constitute an improvement, not because it reduces the height of the warming peak, but because it makes it easier for humans and other species to adapt to climate change, and so it reduces the amount of damage that gets done. The first example, and the clearer of my two examples, concerns species extinction. So one of the expected damaging effects of climate change is that we expect climate change to render some species extinct. How is that supposed to happen? Well, one route to species extinction is expected to be the fact that with climate change, you have the migration of climate zones across the planet. For example, the savanna grassland is going to move as the planet generally heats up. In the northern hemisphere, presumably it's generally going to move northward. And so species that are adapted to some particular environment are going to have to move with that habitat. As the climate migrates, the habitats are going to migrate. The species had better keep up. Otherwise, they're going to find themselves in habitats that they're no longer adapted to and they won't be able to survive. The crucial question then is, well, can the species in question move fast enough? Let's try to predict how fast the climate zones are going to move. Let's try to get some data on how fast we think the species would be able to migrate. And let's look at which of those two numbers we expect to be bigger. So in this bar graph on the right, you have another graphic from one of the IPCC reports. You can't read the stuff on you probably can't read the stuff on either axis. The horizontal axis is labeling various different types of species. The vertical axis is the expected rate at which we think the species in question are going to be able to migrate. So I can't read them either, but if I remember, going from left to right, the species we're talking about are trees, and then herbaceous plants, and then split-hoofed mammals, and then carnivorous mammals, and then rodents, and then primates, and then plant-feeding insects, and then freshwater mollusks. Okay, and the vertical axis goes from 1 to 100 kilometres per decade. So the plants you've got there, the trees and the herbaceous plants, are expected to be able to migrate, like the median estimate is roughly 1 kilometre per decade. The split-toothed mammals are a bit better off. They're expected to be able to migrate at about 90 kilometres per decade. That's the median estimate, although there's large uncertainty about this. And the other species on this graph are somewhere in between. How fast do we think the climate zones are going to migrate? Well, we think maybe 10 to 20 kilometres per decade, but could easily be as high as 70 or so. Therefore, there's a real possibility for many of these species that they won't be able to keep up and they're going to go extinct. Why is this relevant from the point of view of my argument and the discussion of population size? Well, it's relevant because if the rodents, say, are able to migrate at a rate of 12 kilometres per decade, that's not a thing that's going to change if you change the population size. That is a migration rate that is fixed by the nature of rodents relative to physical time, not relative to population time. They will not suddenly become able to migrate twice as quickly just because you've put twice as many humans on the planet. So if you slow down climate change then in physical time, even if you don't slow it down in population time, you've improved the ability of these species to keep up. You've increased the amount of adaptation that can occur, and so you've decreased the amount of damage that results from climate change, even if you haven't reduced the eventual number of degrees of warming that we get to. Okay, so second and slightly less clear example, agricultural outputs. Another route by which we expect climate change to generate damage is via reducing agricultural outputs. For small amounts of warming, the carbon fertilization effect might be helpful from the point of view of agricultural yields. But for temperature rises of more than about 2 degrees, we expect significant decreases in the yields of several key crops, including wheat and rice and maize, and so forth. What kind of process would constitute adaptation to this kind of change? Well, presumably what we need to do is to find or genetically engineer new and different crops which are better adapted to growing in the new climate regime. What does that adaptation process look like? Well, in part it's a thing that's carried out by people, of course. People are going to be doing the experimenting, people are going to be doing the research and development work. And from that point of view, insofar as we're talking about physical time, you'd expect adaptation to proceed faster if you've got more people, right? Because if you've got more people, then you've got a larger number of people, and indeed probably a higher proportion of the population employed in research and development. So this looks like increasing population sizes might be good. However, there's also going to be a component of this experimentation process, presumably, that is constrained specifically in physical time, because I take it one of the things we're going to need to do if we're trying to develop new crops that are better adapted to a new climate regime is we're going to have to try actually growing the things out there in the field. And insofar as you can only do that once per growing season, you can only carry out one round of experimentation per physical year. So again, this might be a way in which the process of adaptation, the rate of adaptation, is constrained by the nature of the causal process, specifically in physical time. Again, if you double the population size, you don't suddenly make it the case that we can carry out 2 rounds of experimentation per physical year instead of only 1. So this is a reason for thinking that adaptation, insofar as it proceeds at a fixed rate in physical time, it could proceed more quickly in population time if we reduce instantaneous population sizes. And so it could reduce the amount of damage that results from climate change if we reduce instantaneous population sizes. Okay. To summarise then, what I've tried to argue is that contra the Parrot Argument, which focuses specifically on emissions rates and the fact that in one sense, if you reduce population size, you reduce emissions, namely you reduce the total global emissions rates. The sense in which that's true, so the sense in which you get higher emissions when you have larger populations, doesn't have any direct relevance, or doesn't have much direct relevance for the project of optimising the world in the context of climate change, given this point about the fundamental importance of cumulative emissions across all time. I've argued that the more relevant questions, and the ones I think we should be focusing on in this debate, are the questions of whether reducing instantaneous population sizes is also likely to reduce cumulative emissions, not just emissions rates. I've suggested maybe it is, but it's not completely obvious. And the second question we should be asking is the extent to which climate damages are a function of the time derivative of climate change, so the rate of change of the mean surface temperature relative to physical time, rather than just the height of the, like how much warming, number of degrees has occurred at the warming peak or anywhere else. Interestingly, as far as I know, none of the integrated assessment models of climate change uses a damage function, which depends even in part on the time derivative. They all just use things like functions that are quadratic in the amount of warming that's occurred. Therefore, none of these models will be able to capture this effect I've been talking about when I talk about adaptation, even though I take it everybody knows that the time derivative is actually important. But if nobody's bothered to incorporate it into the models, I'm just saying notice that you can't find out the answers to the questions that I've been asking by blindly running the models, because you're going to have to carefully set up a model in a way that makes it able to capture these kind of effects, and the way it's set up at the moment will not do that. Okay, so I don't think these questions which I've argued we should be focusing on are completely intractable ones, but they're not just matters of basic mathematics. This is not just about noticing that we're multiplying one number by another, so if we reduce one of the factors and hold the other one fixed, then we've reduced the product. What's going on is significantly more complicated than that. So in final conclusion, maybe I should just flag a few things I haven't considered in this talk. So in some sense, I've been talking about the question of whether it would be a good thing to reduce instantaneous population sizes. But I want to flag that I have only been talking about the contribution of climate change to that question. If I really wanted to know whether it would be a good thing overall to reduce instantaneous population sizes, I would also have to consider other effects of the instantaneous population size on average well-being levels, so that this would include both the straightforwardly economic effects, economies of scale, diseconomies of scale, and so forth. And it would also include other aspects of environmental degradation aside from climate change. The other thing that I crucially haven't talked about, except very briefly in a couple of sentences on that slide about why I wanted to restrict to the climate era, is I haven't talked at any substantial level about what the effect would be of reducing the instantaneous population size over the short to medium term on the number of people who ever get to exist. This is important because from the point of view of certain perspectives in population ethics and perspectives that many of us find extremely plausible, this last effect is actually quite likely to be the most important one. So my conclusion is not then that it would be a good thing overall to reduce instantaneous population size, but it is that probably considerations of climate change favour doing so. So I hope to have at least clarified the shape of the climate change-based piece of this puzzle about jigsaw puzzle about what the optimum population size should be. Thank you.
Okay, well, we now have half an hour or so for questions. I'm going to try and keep it queue and be fair to all parts of the room. Hilary is going to do all the hard work. So let me start with the gentleman over there.
Okay, two questions. Can you go back to the slide that says first possibility? Right. Okay. You have this sort of claim here that planet supplies a fixed amount of various renewable energy types per unit physical time. Isn't that also true of non-renewable energy types? So if you had a growth of population at a fixed point of time, you're going to have more competition also for fossil fuels, which might drive the price of fossil fuels up and prompt a shift toward alternative energy. And correspondingly, you're probably familiar with the green paradox claim that a fall in fossil fuel prices will lead to people using more of them. Otherwise. So it seems to me like in either case, whether it's renewables or non-renewables, more people at a given time is going to mean more use of those sorts of things. It's going to have an effect on price levels and perhaps shifts on how much the proportions that people use. So that's my first question.
Can I do the first question before you go on to the second one?
Okay,
Otherwise
sure.
I'll get confused.
Okay.
Yeah, so the basic point I was trying to make is that fossil fuels are a matter of a stock, whereas renewable energy sources are typically a matter of a flow. So, the fossil fuels are sitting there in the ground. We can use them up over time. If we have more people on the planet at a given time, then we use them up faster in physical time. But that might just be a matter of, if the next 6 billion people live over a shorter space of time, then no surprise perhaps that a given amount of fossil fuel gets used up over a shorter space of time. But it's not a case where the planet itself is saying you can only use fossil fuels at rate X per unit physical time. You can use them, as far as the planet's concerned, you can burn the coal as fast or slow as you want. It's just going to sit there and gradually be used up until it runs out. But not so for things like solar energy.
Okay. The second question, the next to the last slide, just before you get to conclusions. I was struck that, you sort of say that this buys us adaptation time. The other thing...
Sorry, I see.
You're saying that if you stretch it out, the smaller population and so forth, this buys more time for adaptation, which makes sense. Another factor I would have thought you would include was it buys also more time for alternative energy research to make breakthroughs.
I sort of put that on the slide, the previous one actually, but didn't really talk about it. I'm not sure it does in a relevant sense. Sorry, have you finished the question? I should let you go on if you want to.
Yeah, well, it just seems to me like making those breakthroughs is probably both a function of, it is to some extent population time. More people may mean more breakthroughs, that's what I think it may be. But surely it's also a function of physical time. More physical time probably helps.
So I think this case is much less clear, which is why I kind of skirted over it. Here's the stuff I would have said if I hadn't. So the crucial question I think here is, if you, say, increase the instantaneous population size, so if you cram the next 10 billion people into a shorter space of physical time, do you speed up, slow down, or leave pretty much the same the pace of research and development progress relative to population time? Again, it's kind of obviously going to speed it up relative to physical time, but I don't think that's the thing we care about here. Because what we care about is, do we get ourselves off carbon before, say, the 10 billionth person has done her carbon burning, when otherwise we wouldn't have. This is a question of population time. And when we're asking, once we've agreed that's the relevant question, it seems to me we're in a situation where we can think of some reasons that point in each of two directions, and it's not clear to me which set of considerations wins out, although probably some clever economists with a more sophisticated model could say something more intelligent about it. The considerations that kind of leap out at me are, on the one hand, this is a thing I did allude to, presumably because of economies of scale elsewhere in the economy, in the non-research and development sectors, my guess is if you increase the instantaneous population size, then you increase not only the number of the people, but also the proportion of the population who can work in research and development. So, maybe previously it was 10%, now you increase total population size, you're able to be more efficient as a result of economies of scale in your manufacturing industries, so now maybe 12% of the population can be employed in research and development. So this would be a factor that favours thinking that the pace of R&D relative to population time would tend to speed up as you increase population sizes. On the other hand, how does the process of R&D work? Well, sometimes it works by learning from previous R&D experience. So not always, but sometimes. So from that point of view, there are going to be advantages to carrying out different R&D projects in series rather than in parallel. And that's the thing that you're able to do to a greater extent in the case of smaller instantaneous populations, spreading the whole thing out more across physical time. Okay, so now I've got two competing considerations that point in different directions, and the question is just which one is bigger. Outside my area of expertise, haven't got a clue.
Thank you very much, Hilary. You've done, in this paper, you've been talking about population change, but you've done the kind of standard population axiology thing of considering population being a relatively static concept, the instantaneous population size. Whereas when we actually talk about population change, of course, we're talking about population dynamics, and in particular, the birth rate and the life expectancy. If we want to reduce the population size, we either have to reduce the birth rate or reduce the life expectancy. And if we're talking about expanding population, we're talking about either an increasing birth rate or an increasing life expectancy. And these dynamic effects do also have their own impact, which I think adds to the kind of considerations that you were talking about in the end of your slide.
Yeah, that's right.
Because obviously, if you reduce either the birth rate or the life expectancy, you end up with more adults as a percentage of the population, which on your model means more change makers. And not only that, but you also mean that more of those adults don't have caring responsibilities, either for children or the elderly. So more of them are then able to devote their time. So I think there is another set of considerations that might be worthwhile putting into this, of actually considering the dynamic population model, and that maybe we don't want to reduce population size because we actually want to reduce the number of people, but just because we want to free up more of the population for being adults without significant caring responsibilities who can then act to bring about the change that we need now.
Okay, yeah, so I think it depends whether, I mean, you're absolutely right, I should have included those somewhere in the talk. The question is, can they basically be contained in this last bit of things that I quite legitimately didn't talk about, or should they have also occurred earlier in the talk? I tend to think that to a first approximation, they can be in the things legitimately not considered in the talk, because I think mostly the kind of things we're worrying about when we worry about population dynamics are not really about climate change. They're more about the effects on economic growth in developing countries and so forth. So they're in this bucket of things that affect average well-being levels. I mean, you're right, of course, that I was saying that a number of people who can work in research and development is one of the things that's important for the purpose of climate change. And of course, this stuff about dynamics, insofar as it frees people up from from caring responsibilities, also affects the number of people who can work in R&D. So that's the reason why I can't completely ignore it. But I'm going to hold out hope, I think, to keep things relatively simple, that to a good first approximation, I can ignore it, and that other factors in the already quite complicated calculation I was sketching in reply to Matthew's question are going to be larger. That's a conjecture.
Question in the back.
Yeah, hi, thanks for your talk. So I'm not a philosopher at all. I do climate policy and international law. And I just want to ask, you have these three assumptions and then you make a conclusion from them, but you basically then disprove the two assumptions, which means that your conclusion doesn't hold anymore. I mean, what's the point of this? Like, what should I be taking from this? Basically?
Okay, good. So the point of this was not, I am assuming these things and so this is my conclusion. What I'm trying to do is refocus the debate. So I think it's important to notice that if these things were true, then that conclusion would follow. So insofar as we don't think that conclusion follows, we must be committed to the view that one or more of the assumptions of this simple model is false. And then it's helpful to talk about which one and why we think it's false. This is not the thing that gets focused on in the population debate at the moment, because people are looking at basically Parrot's simple argument and saying, look, this is just a matter of basic arithmetic, it's totally obvious, we don't need to ask any deeper questions. So I'm saying, insofar as you're interested in arguing or working out whether reducing population size would help with climate change, these are the things that we need to be having the discussion about. Does that help?
I mean, a bit. Yeah.
So the point is, we don't just want to get to the right conclusion, we also want to know what the argument is for that conclusion. And this is supposed to be a tool that helps us do that.
Okay.
Martin?
A question about discounting the future. You mentioned that, in a sense, one shouldn't discount the benefits to future humans.
Yeah.
But in practice, as we know, the probability of climate change is because the downsides seem a long time in the future by human lifetime standards. And if the population goes down, then the downsides will be even further in the future, so people will be less motivated to do anything about them. So isn't that a possibility that, in fact, less effort will be made to develop clean energy and all those things, because people think that the downside, if we don't do that, is further in the future, and people do, in practice, discount the future?
Yeah, okay. So I was obviously talking at the level of normative or evaluative theory. Is it kind of ethically correct to discount the future? And I'm saying no. So you're pointing out a different thing, which is never mind that maybe it's an ethical mistake. People do, in fact, do this thing. Yeah, in principle, that would be a thing you would want to take account of. It depends how irrational/immoral you think people are. My guess, actually, is that they're not just irrational/immoral in the sense that they discount the future. They're sufficiently irrational/immoral in this domain that they probably wouldn't notice the difference between the very far future and the very, very far future, so that this effect wouldn't result. Does that sound plausible?
Martin, did you want to come back and say whether it sounded plausible or not?
Sorry?
Did you want to come back and say whether it sounded plausible to you?
Well, I do think people care about the lifetime of themselves or their children or grandchildren, and are less concerned about what happens beyond that. But of course, people are irrational, because the example I like to quote is that in talking about radioactive waste disposal, people talk about whether the depository is safe for 10,000 years. That's one context where people do apply seriously, right? So people are very irrational. But just another point about the pace of R&D. I think there are some contexts where the pace is pretty independent of the population. Let's take fusion. I mean, it may never happen, but there is a definite sort of roadmap for what ITER will do and what will happen, which could in principle lead to fusion in 40 years' time. And I don't think that time scale would be changed very much, whatever the population was, provided we agreed it was worth doing one big R&D project somewhere in the world on fusion, because there's a natural time scale.
This is the case where it's important to do it in series. You can't just break the project up into chunks and do them in parallel. Right. Okay, thanks.
Karen?
Yeah, so I'm also somewhat on this R&D point. So, I mean, it could be that we reach a point, maybe fairly soon, where we don't really need that many humans anymore, even in R&D. I mean, suppose that we really have massive progress in artificial intelligence or something like that. Then it seems that your argument seems to suggest you really should bring down population size.
Well, it depends how optimistic you are about safe
sure.
AI. I mean,
It all depends
if
on
they're
the
also going to
yeah.
get us to zero carbon like that, then have whatever population size you want.
But it might be that we have exactly this delay, so I mean, we might have this decoupling, R&D will ultimately solve the problem, but we might not need that many humans, and we should bring down population size now. Then in the future, maybe we can ramp it up again. It doesn't matter anymore. bringing it down now might be a good
Yeah,
idea.
I mean, I
While
guess for the
users
duration
less
of
consumers.
right, for the duration that the AI, the nice, friendly, safe AIs need to figure out the answers to all our problems for us, I guess that would follow.
Something of that sort. Yeah, of course that's also wildly optimistic. Yeah.
Yeah, I mean, insofar as we're talking about AI, I think like population size is the least of our worries.
Fair enough.
Yes, and then the person behind.
I'm sorry I came in late, so you might have covered this already. And it's not going to be starting the original. But doesn't it also matter how the global population is spread spatially? And just as some species are going to have trouble adapting fast enough, some human population groups may too.
Mhm.
And then there may be increased conflict over water, access to food, health problems, migration, and a lot of resources could be diverted to either putting up walls to prevent that migration, or peace efforts, or humanitarian relief. So the spatial aspect surely matters too.
Yeah, so I mean, I didn't intend by any means my list of examples of adaptation mechanisms that might be constrained specifically in physical time. That list was not supposed to be exhaustive. This was just, I can establish an existential claim that some such processes have this property by giving you a couple of examples. And sure, I mean, things that are true about species in general are also true of humans. Yeah, I mean, maybe putting humans on this particular graph is not plausible because the the possible human migration rate is not really the relevant thing, and you just get on an aeroplane, that'll fix it. But there are more complicated routes by which various aspects of human adaptation are constrained in physical time, and this was supposed to be one example of that. But as you're pointing out, that you could think of at least 20 other examples and think about the details of how each one of them goes.
Well, yes, getting on a boat across the Mediterranean isn't necessarily very easy.
Sure.
Yes.
Thank you. So this might be more a question of understanding, but I was puzzled by premise 2, so that peak temperature is only determined by overall emissions. I was really puzzled when you gave the playground example, because the difference between the playground and the atmosphere seems to be that greenhouse gases stay in the atmosphere for a certain amount of time and then they're absorbed, whereas the playground doesn't regenerate in the same way. And I mean, you have the data there, but I would have assumed that if you spread the population really thin over a very long time, that then the atmosphere has enough time to regenerate, and that would make a difference.
Yeah,
so I'm surprised by that.
So this is what the sort of thing I had in mind when I said, although I'm not going to question the second assumption, you could do that kind of thing. The reason I didn't question it is, as you suggest, sort of, in your question, I think the magnitude of the changes in instantaneous population size you would have to be talking about for that effect to become significant are probably pretty extreme, and they're probably wildly beyond the kind of things that we could obtain by, ramping up funding for family planning programs and so forth. I mean, generally speaking, we're mostly focusing on carbon emissions here. They're responsible for the majority of climate change. Carbon is pretty long-lived in the atmosphere, which I take it is like the physical reason why the climate models that Alan and collaborators run generate the result that they do, that cumulative emissions, to a very good first approximation, is the thing that determines the peak warming. So yeah, I mean, if you did the Alan et al. Modelling experiment with a bunch of emission scenarios that had the same cumulative emissions but differed massively on the emissions timing, then you might invalidate their results. But then my guess is those kind of massive variations in emissions timing are probably not the scenarios that we're interested in anyway.
Yes.
Thank you for the talk, super interesting. I'm also not a philosopher, my background's psychology, so this is quite a small question, but I mean, also feedback on the playground isn't regenerating itself, whereas the planet kind of would be. You said that the migration rate of species is an intrinsic property of it, and it's not, it's a very important function of what their surrounding environment is. Is it natural habitat, is it agricultural, is it urban? That will affect their migration rate, and habitat loss kind of is interacting with climate change, but that is the main driver of species extinction, and that is affected by the number of people who are on the planet, particularly for like...
Okay, sorry, I need to slow you down, I'm getting confused here. So I didn't say, or I didn't mean to say, that it's the rate at which a species is able to migrate is an intrinsic property of the species, in the sense that it's not affected by any other factors other than the identity of the species. All I was trying to say was, it's a thing that's pegged, insofar as it's a rate that's fixed in time. Okay, fix all the other contextual parameters that are relevant, then you've got a rate that's fixed in time. Which kind of time is it fixed relative to? answer physical time rather than population time. That was all I was trying to claim. So, you know, from the point of view of thinking in terms of this distinction between physical time and population time, the question that I was wanting to focus on is, you know, is there any reason for thinking that merely slowing down climate change in physical time would make things better if it didn't slow down climate change in population time? That is there some reason here why we should care specifically about this type of time rather than that other type of time? And the answer is, well, yes, among other things, when you start thinking about adaptation, because of this reason. So I didn't mean to deny the stuff about other contextual factors also being relevant.
I think also the physical time, maybe not just for climate change, but for resource use. So for sort of we're running out of soil, we're running out of kind of fish, and that is happening. I guess it's just a population time, but having physical time to recover as well.
Right.
Person in the blue behind Martin. Martin, then you're next.
Thank you, Hilary. It's really delightful talk to listen to, and really great to introduce time into this kind of debate. I feel it's brilliant. So, now taking physical time, this is very theoretical here, is that people become more aware of these issues, which then they kind of has a cascading effect upon what you were saying, this population time. This can be almost like a feedback loop, because people are becoming more aware, they can make their own decisions and choices, which actually could start to reduce the carbon emissions, for instance, on a larger scale. Do you think that would be important consideration in your model? I mean, it's highly complicated, and I can see what you're trying to do, and I can understand why you simplify it.
So let me just check I've understood you correctly. Are you saying that an important factor for how successfully we deal with climate change is how quickly do people start caring about this thing more, and that rate is likely to be, to at least some extent, fixed in physical time? Is that the thought?
It won't be fixed, though. It depends, I mean, kind of...
Or at least
what
constrained
Martin was
by...
saying is how quickly things are going to escalate, how quickly things will get worse, right? Because, I mean, if things are getting bad quicker, then people are going to make changes quicker, right? But if we reduce population, we increase the time of actually having to deal with these, then maybe we won't make a self-aware decision.
Yeah, but so the relevant question is going to be, okay, granted that people might become, like, start taking the problem seriously at a slower rate in physical time when we do this slowdown, do they also become more aware at a slower rate in population time when we do this thing? So insofar as I can make any conjecture here, my conjecture would be they take it more seriously, well, they increase their degree of caring faster in population time when you slow the thing down in physical time. And the reason for that conjecture would be part of the process that leads to people increasing their degree of caring is a kind of sequential discussion, which maybe happens at a rate that's somewhat fixed in physical time. Like, for example, the 5-year period of the election cycle might be one relevant parameter, and elections are not going to suddenly be held every 4 years rather than every 5 because the population's got larger. So there might be that kind of effect. I suspect it's a pretty weak effect, but again, I don't know. Yeah, I mean, mostly the point of this talk is like, these are the kind of things we should be thinking about, not I have the answers.
I just wonder how much policymakers are going to be influenced by this, because as we all know from the IPCC graphs you had at the beginning, things could get seriously bad by the end of the century, triggering irreversible things like melting of Greenland's ice and all that. But over this century, unless something really terrible happens, the population is fairly predictable, isn't it? I mean, it's going to rise from the present value to nearly 9 billion by mid-century, if the people now young have a lifespan of 60 or 70 years. That's causing the rise between now and 2050. And what happens beyond then does, of course, depend on policy choices, but there's no scenario other than a really disastrous one, which could bring the population by 2100 lower than the present population. And so I just wonder if any of these considerations will have any relevance on the timescale where we need to act.
Okay, so insofar as you're sceptical about that, I take it you would also be sceptical of paying any attention to Parrot, because you're saying, well, you know, look, Parrot, if maybe if insofar as the simple argument is correct, yeah, if you could significantly reduce population sizes, maybe that would help. But this is just not a thing we could do on the relevant timescale, so let's not bother talking about population size at all.
Well, I think we should talk about it, because obviously, if Africa's population doubled between 2050 and 2100, that may have bad consequences for the world in other ways. But it's not going to have a major effect on these. So I think it's going to be the transition to renewable energy, which is going to be the main determinant of how CO2 gets. I think in the long run we might want a world with a lower population, but all I'm saying is that unless there's some real disaster, the population isn't going to go down enough to make very much difference to these arguments until well after 2050.
Okay, good. So, I mean, there are two things you might be saying there. You might be saying, from the point of view of the, actual evaluatively correct arguments about what we ought to do, we might as well set aside population for these reasons. But I noticed that in your initial question you asked specifically, does this have policy relevance? So another thing you might be saying is, well, yeah, if the policymakers were ideally rational and morally perfect and all that, then maybe there would be some relevance. But because they're somewhat myopic and they're not going to be willing to think beyond the end of the century, they're not going to listen to the only kinds of arguments that we're going to be able to come up with. And I'm not sure which of those two directions you wanted to go in.
I think there are arguments in the long run for reducing population, but they're probably not climate arguments, because the fate of our climate is going to be settled during this century. Whereas the climate, where the population changes to a much, much lower population, would be well into the next century, I think. So,
well, how
so dealing with climate, I'm not sure that population trends are going to be.
So how clear is it that the climate issue is going to be settled this century? I mean, you might think, if we're going to avert really bad outcomes, then we better have got to zero carbon by 2100. However, there are bad possibilities that are worse than other bad possibilities, and it's possible we don't do that thing. So for those kind of reasons, I would have thought, even if the population effects would only kick in after 2100, they will still make differences to the expected badness of what we get climate change-wise with this or that population scenario. Sorry.
Do we have any other questions? In that case, I'd just like to ask you to join me in thanking Hilary for a wonderfully clear and perceptive talk.